Okay. So all good with the homework. We extended the deadline until Wednesday, so you have a ton of time. My office hours will be this week will be Friday at 2 to 3 p.m. and we'll see if this time works for everyone. I mean, there's a higher chance for me to be unavailable on Friday, so I would prefer to do something like Thursday or Tuesday. But this week it's 2 to 3 Friday, and it's on Zoom, so you will be able to just connect. And if you have any questions about homeworks, about the homework, go for it. And TAs also have office hours, so they are pretty knowledgeable. They will be able to help you as well. So if you need help, just go talk to them. Especially, I mean, I know that graduate students are quite independent. Undergraduate students might have issues. So who is undergraduate today in this class again? Not too bad. I mean, but not ideal, obviously. So apparently people prefer not to show up in person, but I appreciate people who do show up and ask questions, obviously. Okay, so our topic today is back to linking and loading, right? Again, we're just like a couple of lectures away from booting the operating system kernel, from understanding how the kernel is compiled, linked, and then loaded in memory. But those lectures will be kind of intense. Maybe not today, but next one will be a little bit hard when we'll be talking about position-independent code. Just to quickly remind you what's going on here is we started looking at the layout of the memory of the address space of a process, right? And we said, okay, look, a couple of those areas get loaded from disk. They get generated by the compiler and linker, global variables, text of the program, and areas like heap and stack are just created at runtime by the operating system itself, right? And I showed you an example of this simple C program, which again I compile with this command, and we already know what it means. Then I used my favorite tool, objdump, to say, okay, show me all the sections of this executable file, which is, by the way, is packaged as an ELF container, and it has a text section. So, for example, this instruction 55 is right exactly here in the text section, right? We have a couple of other sections: read-only data for read-only variables, data for writable and readable variables. We don't have this funky BSS section, but we'll see it later. And so we look through this, we understand, okay, look, it makes sense. Those instructions are exactly where we would expect them in the text section. They are aligned. We understand that, okay, if we compile the program, it sits on disk here in the ELF file. We'll take a look at the ELF file, I think, early next week. And your homework will be actually to build a tiny loader. So essentially, like a tiny toy loader, which will be reading this ELF file and loading it in the memory of the process and running it, right? So simple, but that's what we plan to do. And the main goal for today is to understand how these programs are compiled from multiple files, right? So this is an example of a make file used by a x86 operating system to compile something what is called a boot block. And those names are just whatever. They're human readable names. They're called targets in make file. You can put foobar here. It doesn't change the logic. What really matters is those input files like the bootasm.c and bootmain.c and the logic of these commands, right? So, and I was kind of wrong. I was saying that these two were the inputs, but in practice, these two are the inputs from which this bootblock.o is linked, right? So this is a -o means that the next argument is an output file, right? Okay, so at a high level, not as hard, right? But let's take a look under the hood, right? So again, this process of getting the binary, getting it running in memory consists of two steps. One is called linking and one is called loading, right? So linking, naturally, what you can guess is the process of combining multiple object files into a single executable, or maybe a single library, right? And loading is the process of final step of which operating system says, okay, like I have this executable, but maybe my memory layout is slightly different, and maybe some libraries are still missing. So we will still do another merging step, load additional libraries, and then maybe move the program a little bit in memory. But let's take a look at linking first, right? So it's very much represents this make file, which I was just showing on the screen. So there is a program which is called linker, right, which is provided typically as your part of your compiler tool chain, right? And it takes as input those object files, right? So remember, my GCC minus C flag means compile but don't link, right? So if I say main.c, it produces main.o object file, right? So this is the object file. We looked at it, right? So text section, read-only section, stuff like that. That was my example, right? So you can take multiple of those, right? Because you might be working on multiple files like foobar.c and stuff like that, right? Along with some shared libraries, for example, something like, I don't know, maybe you generated a printf function, which comes as the library, right? Maybe not you, maybe someone else, like you get the library from somewhere. And I don't really know why this picture says shared libraries and normal libraries, but let's say shared and dynamic libraries, right? Or something what is a little bit more flexible. We'll take a look at what these two kinds of libraries are just in a second, right? So I will explain what it means, right? But maybe this is like libc library, right, which is provided by the operating system. So you can have a malloc, for example, and a way to invoke system calls, right? You can also provide some control files, and x86 uses them, which might specify how to link this program. There might be like specific requirements which you want to specify, and typically you provide command line arguments. Like in my previous example in the make files, this linker, which was abstracted by the LD variable, right, and in shell in my make file script was taking some command line arguments. And what the linker produces, it will produce first of all, like the compiler itself will generate debug info here, and the linker essentially can preserve it as well. It might provide an executable file, which might be running on your system, or might be linked into a library, and like will provide some additional information which will allow, again, if it's a library, you link it again with something else at the next step, right? So again, roughly speaking, well, nothing super interesting, just a bunch of steps, right? And that's essentially the slide which summarizes those steps, right? But if we take a look at what's going on here, just at a high level first, let's imagine we have an object file, again, maybe it's a main.o, which, I mean, here they call it A, right? So it's, let's say, a.o. Calls functions B, C, and D, and there is an object file B, which calls C and E, right? And like linker says, okay, cool, I will take those two libraries as input. I know that C and D are provided here, and essentially we'll take A from here, B from here, C and D from here, and E from here, right? And we'll essentially merge them together and output an executable file, right? Not super hard. If I ask you a question, so why linking is so important? So what would be the reasons? And I mean, again, you need to have a little bit of a historical perspective here. So you can, today we deploy in terms of containers, right? So which are, I mean, giant blobs of everything, just to make sure that all the dependencies are satisfied. But back in the days, they have limited memory, limited disk. So what steps do you think linking can address?
Smaller executable files.
Small executable files. You're right. So for example, and it's a great example, I will show it later. So but for example, if the operating system has a ton of dynamic libraries, right? So those are called DLLs on Windows or shared objects on Linux, right? So which implement maybe malloc, implement printf, implement your libc, which is an interface to invoke syscalls, for example, like and all sorts of things. Your main .c compiles into some kind of an executable. Let's say maybe it's a cat, right? And this cat is really, really tiny, because what will happen when the operating system will link and load this program? It will, I mean, you can do that at a linking step, and you can say, okay, linking, there's a linker, and please take this cat, those libraries, and maybe produce a static binary, which essentially includes the logic of cat itself and all this additional libc, printf, and so on, right? So in malloc. And that gives you quite a big executable, right? So because you say, okay, look, I linked everything, put it on disk, right? So this might be like, I don't know, like maybe like 1 megabyte. Although this guy is probably roughly under 1 kilobyte, right? But you can play a different trick. You can say, look, I'm so fancy that instead of doing this step statically and producing this executable, there will be something what is called the loader implemented by the operating system, which will say, right when you do an exec, for example, and you say, look, I wanna load bin.cat, the operating system understands that, okay, this file is actually missing dependencies. And right at this step, without actually putting anything on disk, it will create an address space, right, for a process, which will be from 0 to 4 gigabytes. It will load cat here, and it will resolve those dependencies, saying, okay, look, I'm missing libc, for example. It will load libc here. It will load maybe malloc here, and printf somewhere here, right? Which will, like, in a program, absolutely, right? So they do occupy space. Maybe they do occupy the same 1 megabyte in memory, right? But at least on disk, the cat remains 1 kilobyte, right? So it allows you to save the disk space. However, as you can guess, there is a trick, and the trick is the following. So if you say, look, I have another program, let me change the color to blue. And maybe it's not cat, but WC, right? And again, you skip this step, statically linking WC with all these libraries. But when exactly when you do exec of bin WC, the operating system says, okay, I get it. So WC also has dependencies on those shared libraries, right, or dynamically linked libraries on Windows. And what it will create an address space for WC. And so there will be a WC here sitting here. But what will it do instead? It will reuse the same memory for those libc, printf, and malloc, and use them here in the address space of WC, which will allow you to essentially save, like, load these libraries once and pay the price of 1 megabyte. But for each additional, and it will be 1 megabyte of physical memory. But since there will be a mechanism which will allow you to share physical memory across multiple processes, right? So this is like P2, and you loaded P1 earlier. So the price will be paid once, right? So you can also save memory by essentially sharing libraries across multiple processes.
If cat depended on WC, would it store WC in the on the drive as well, or would it load it at runtime?
If cat would depend on WC, so essentially like the distinction between a library and executable is kind of blurred to a degree. And so if the cat has a dependencies like this, and you say, look, cat needs WC, you will load WC here. And I think there will be some accounting mechanisms saying that, okay, look, I really need. So, okay, that's a good question. And to be honest, I don't know the answer. So because those are executable files and those are libraries, right? Shared objects, SOs. I can imagine that there is a way to make sure that you can depend on an executable file, but I never seen it in practice. So I'm pretty sure that in some hacky way you can do it. You can because essentially inside it's almost the same. You can, roughly speaking, if you're very careful and you play these tricks, you can make sure that it's either a library or an executable. Executables, you start with exec, right? So the second time you will invoke exec, it will still load WC here, right? So it will be a new address space. So most likely you will end up with this layout in which WC sits here if it's just a library, and if it's an executable, you will end up sharing those libraries in between. You will see a little bit okay. So I think towards the end of these 2 lectures, you will understand that those tricks are probably possible. I don't think that anyone implements them in practice, but I can be wrong because people do hogs. I don't know, but why did you ask? Why is it important, do you believe?
Oh, I think I had it mixed up with you make a makefile that links to 2 objects.
Yeah, so makefile is kind of like an ultimate tool. This can break any rules you want. So you say, like right now we work with object files, but those are L files, and you can say, I'm pretty sure you can, like, if you really want, you can put something like WCO here, and it will work. I don't think linker will care much about the fact that maybe it's a shared library or something like that. It's an L file. It has all the information to be relinked and used in this process, and you can play this trick. But again, let's just go one level down. You will be able to understand, but and like maybe it will become clear. Okay, but 2 main things I was saying, which we have to observe from this drawing, is that you can save space on disk, and you can later save space in memory, right? By sharing libraries across multiple processes. Are there any questions about this?
So is it correct to say if we want to fetch our libraries?
Is it correct to say before?
We want to fetch our libraries?
In a way, yeah. So operating system keeps track of what libraries are already loaded in memory, and it will try to reuse them if they are required again during the loading time. Is that what you're asking? An interesting problem arises is, what if you depend on a library, and let's put it this way. Let me change the color again. Let's change to green here. What if you depend on a library which is already loaded in memory at this address? And imagine it's a foobar or full library. This space is already occupied, so you cannot really reuse it here, right? Because there is some kind of a conflict, right? Because you say, look, I loaded foobar at some address. I want to use it again, but maybe this address is already occupied by libc or printf. Maybe the green process which was running here said, okay, I don't need libc and printf, I just need foobar. So what do you think? How can you solve this problem of an address conflict between libraries which you want to share across processes? Add foo at the end. And maybe we didn't yet talk much about it, but imagine foo has a pointer to a data section, right? So clearly this pointer will be different depending on where you put it in the address space, right? So if you want to use foo here, then you need a different entry, right? Because you need a different you need a different pointer in the code section, right? I agree. Is it too hard right now to understand? So like we'll come back to this again, but this is an idea. So there are two ways to solve it. Either you say I have a global registry, some kind of a global knowledge about where all the libraries can be placed in memory, and I make sure that there are no conflicts. And I think Windows was using this approach, and it was reasonably successful. If you control the library space, you can just assign them random addresses or like assign them addresses from a specific ranges and make sure that they don't overlap. However, of course, like it's not ideal. And the real solution is this idea of a position-independent code. Position-independent code allows you to generate a code which avoids changes to this pointer. Works a little bit like magic. So it uses a collection of tricks to make sure that no matter where you place this binary in memory, it will still run. And I will explain how to generate this code and what these tricks are doing, right? But I just wanted to provide a motivation for why it's needed, right? Okay. So, but back to my kind of line of exposition, trying to essentially motivate like why we need linking. So there is a couple of other reasons. So typically we like to write programs as collection of modules, right? So some languages have an abstraction of a module, right? So which has like visibility rules, and those things can control what is accessible, what is not accessible, but also it's just like easier to reason about code this way. We can also, by the way, if you change one C file, the make file is smart enough to track that only one C file was changed, and it will recompile just this one source file because other object files are not changed, so it will save you time with linking and just relink the executable. The truth, however, is that this linking step can become so painful. For example, linking the Linux kernel, depending on the machine you're using, can take from like 15 minutes to like an hour if you're unlucky. So because it's just a giant piece of code with tons of executable files, right? And like there are projects which are even worse. So efficient linking is still explored. So like the C toolchain doesn't have a very good linker. And those arguments of space efficiency, essentially, like you can share common code across executable files, and you can share it on disk and in memory. That's what I was trying to essentially explain. So at a high level, linking, again, like it's not super hard. So you just first scan all the input files, trying to identify what functions are unresolved, meaning that have to be provided from some other object files. You identify the boundaries of like the text segment, data segment, and stuff like that. Trying to getting ready to merge them together, right? And then just essentially in a second pass, you just merge them, patching the addresses, making sure that they point to the right locations, right? So again, just to show you a couple of those examples, we have module A, originally maybe compiled to run at address 0 from 0 to 600. Module B, again, compiled to run from 0 to 400. Module C, compiled to run from 0 to 500. When you do link them, you just, oh, that's beauty. Sorry, pan. When you link them, you just merge them. If it's, for example, a text section, you merge them, maybe leaving A starting from 0 to 600, but B starts from 600 to A00. And so C goes from A00 to F00, right? So literally merge, right? If I like slightly more detailed figure here, you literally do that with all sections. So you say like there's a text section, a data section, there's a better safe space section for global variables initialized to 0, right? So you say, look, I will take the text section from all object files, A, B, and C, merge them together here, and they will form a single text section, right? Same with data. So 1, 2, 3, merge them together, get the data section. Same with BSS, right? So again, intuitively easy, right? However, if I ask you a question, so what needs to be done to the code here to make sure that it still runs correctly after merging?
You have to sort dependencies so that things that already have things dependent on them go first.
Correct. So for example, if there is a function foo, which is provided here, and you do something like call foo from this module, right? Originally here, you didn't have an address, right? You kind of like, you put some fake address here saying, okay, I don't really know, but at the end of this container, which holds this file, you say, look, I remember that at this spot, I have to really patch the address, right? And so essentially when you call foo, you now have the real address of foo. Let's assume this address is A. You really have to put A here, right? Agree with this? And there's another problem. Okay, that's one. Okay, good. What else? So this first step is finding unresolved symbols. So what can be those symbols besides functions? What else you'll be looking for? What else can be unresolved?
String constants.
Not just string constant, any global variables, right? So maybe you like do a move instruction and you say there will be some magic string or some magic variable, right? And this variable is actually provided here, right? So I don't know, move some kind of a var, and this var is sitting in this data section, right? So you will have to patch this address for this move instruction to correctly point to this data section where this variable space for this variable is allocated, right? And since it's data section, it can be, or it can be BSF, like maybe it's initialized to 0. What I was trying to say, I forgot. This can be any global variable. Agree? So not just string. You were raising hand. Okay. What else? What else needs to, like, good. So we say, like, these are the unresolved symbols. So let's say functions and global variables, right? So local variables are always within the scope of a function, right? So you don't have to, they are always resolved. Dynamic variables, like there's still be some local variable or global variable, which is a pointer to a heap, right? So that's not a problem either. So, okay, so we find unresolved symbols. What else do we have to do with this executable? Let me change the color. No, what else can go wrong? What if you were, like, even in this text file, you were referring to a variable, let's say var2, and var2 was known to you. It was sitting in your data section. What do you need to do with this instruction, which uses your, like, the variable which was resolved? Like, roughly speaking, remember, maybe this was address 0, maybe this one was address 496, right? And this one was 496 plus some delta. But clearly, when we merged the data sections, right? So this variable will be sitting somewhere over here. So 496 might be somewhere over here. So this address can be anything, right? It can be like, I don't know, 16,000 something, right, for example. So it's a different address. So if you had an instruction here, which was using this variable, you clearly have to adjust this address to point to this variable to here correctly, right? So, which means you kind of like, the act of merging is equivalent to act of moving the binary in memory. So because you say, look, even though I knew that this variable is at a specific address, this address can be a different address, right? Agree? Okay, so that's more or less what we want. So, but we just have to be clear that this is what has to happen, right? Okay, cool. So this act of doing it or moving the binary in memory is called relocation. So let's take a look at a concrete example again, just to understand how it works. And I will switch back to red. So imagine we have this assignment. You essentially save A into B, right? So imagine this is the code which you got generated. You say we're using GNU assembly syntax. So A, you first load it into EX register, and then you load EX register into location of where the B is, right? Agree? So imagine you generated the code, but A is defined in the same file and is at the location 1, 2, 3, 4, and B is unresolved. So it's imported from a different file, right? So, and this is the code which you will generate. So this is a 1 byte opcode for this move, right? This is the address for the A, right? Because it was at the address 1, 2, 3. And do we know why is it written in such funky manner backwards? Who can tell me? Yeah, because, well, there are, roughly speaking, two big paradigms. One is little endian and one is a big endian. So essentially, this is the agreement on how to store things in memory, right? And if your memory is growing, so from address A to A+1, A+2, A+3, if it's a big endian architecture, you literally just put them in this order, like this, the top bit of the address, for example, goes at the lowest address, then the next, not bit, sorry, byte, but then the next byte, then the next byte, and then the next byte. This is an example, this example is an example of x86 architecture, which just uses this little endian encoding, right? And the numbers are placed in memory backwards, right? So essentially, if this is your 0, 0, and what did we have? 12 and 34, then 0 goes at the very end. Second 0 goes at the very end too. Then 12, and then 34, right? So that's just how, and there are historical reasons why they were agreeing or disagreeing, which, like, why this encoding, one encoding or another encoding makes sense. Just make sure that you know, like an anecdote here. When I was a student, macOS was using PowerPC architecture. PowerPC was big endian. So my TA was using fancy Mac. So she was like on Power with big endian. My assignments, which I was programming, were on x86, right? So, and you say, well, does it really matter? But it does. So like, for example, we were like, if it's a graph of objects in memory and we deserialize on disk, like everything is upside down to her architecture. So I had to compile the code to make sure that it runs on her machine. Right, so, and it happens in networking because, for example, you know, your sender might be using x86 and, you know, your receiver might be using some other architecture. So, like, you know, if you do a move instruction on one other architecture, it will mean different thing. It will be in the reverse order, right? So again, useful to know, but just a side comment here. Okay, so again, we got this thing. So this is the address which got generated for the variable which is local. For variable B, since we don't have it, so you can put any address, right? And again, the agreements will, like, what is it? Conventions will differ. But in this specific example, we just generate zeros, right? We say we don't know where this variable will be. Let's just generate instruction with zeros, right? But remember somewhere the fact that this address has to be patched, right? Later on, when this object file will get linked with the object file which actually provides B. And essentially, this is what will happen. So assume, again, at the time you link the binary with another object file which provides B, and assume that the data section in which A was located is relocated by x10000, right? So then you say, look, okay, since this address, it has to be moved in memory, as I was saying. So it's a simple operation. You just add this shift, right? So you essentially add this, and by magic, these lower addresses just don't. It doesn't always happen. It just happens in this example, right? So that only the top byte has changed with 1, right? And B now is found at this address 9A112. Again, little endian 9A112, right? 12, sorry, right? So this is the final code after the program is linked, right? And is ready to run. It's ready to run it's linked to be, remember in my make file, I said, please link the text section to run it 7C00, right? And so maybe some other address was provided here. So maybe it stayed 0, right? Maybe it's like 10000, right? Something like that, right? So it doesn't really matter. But the fact that we're linked together and this thing is now ready to run at this address. So the operating system has to load the text section at this address. If it just shifts it by 1 byte, those addresses don't make sense anymore, right? Because instead of reading A, you will be reading partially A and some other part of some other variable, right? Agree with this? Okay, so a little bit more realistic example now. So we have your main function, which has a global variable string, hello world, and it calls a function A on that string. And this is a function which is provided by another file, right? So it's provided in a.c, which implements this function A as writing to the standard output string and saying it's the buffer of string len, right? So I'll ask you a couple of questions. Why do we need this declaration saying that the function A is external? And we actually need a signature of a function. So when you work with C, typically you rarely use extern. So most of the times you just say, that I have a header file, and in the header file there will be void a char signature of this A function, right? But why do you need this information to begin with? Why do you need to know the signature of a function?
So you know what it's going to depend on.
You kind of have this information here. You say, I depend on A.
I guess it would actually be more like what the size needs to be for that function when it's creating a space in memory.
We don't create a space for this function, right? So, and this information doesn't really tell us anything about the size of A. So
no, but it does say the size of char.
It does say it has information about input arguments, right? Or maybe like output arguments as well. In this case, it's a void. So why do we need this information? We don't know what the body of A is. It can be anything. It can mix the string, maybe do some kind of a permutation. Maybe it will just print it on the screen. Right? But why do we need this declaration extra?
Let's the compiler do type checking.
Allows the compiler to do the type checking. Yeah, correct. So type check. And say that if you're trying to put an integer b here, it will reject your program. That's a good argument. What else?
To get the star address of the A function.
We don't have the address of the A function, right? So we literally don't know where it is. We just, like, these are two different files. Maybe this comes to you as a library, like in SO file. I gave it to you and say,
Yeah,
link.
they have to connect link together. So I think the main function needs to know the address about the A.c file.
There is nothing about the address here, right?
Okay.
But you guys were close. You were saying, okay, there is a signature of function tells you what arguments you pass in and what you get back. So why do you need it?
Does it help you know how to not how to see the registers, but how to using all of the I don't know if you report the entire set of the register? All of its register? Kind of
To do what?
well, like if you're using a versus like a long, you need so many bytes out of the register to use?
No, I think you're close, but I'm a little bit surprised that you guys can't really tell me. So remember how we, okay. No, but the name is here, so you have A, right? So you know that later on you have to, okay, so what's under the hood? Again, and partially the reason we're doing it is to understand what's under the hood of, like, you have a line of code. My goal is to, like, I ask you a question, what machine instruction will be executing? So, okay, I'll ask you this question. So when you reach this line, what machine instructions will be executing? Which one? Call? Yeah, some A, which we don't know yet, right? If I ask you which instruction will be sitting here, push. Why? No, come on. Calling convention. Passing arguments. So you have to pass a string, right? So essentially, to generate this call site, essentially, you need to know what arguments you are passing here, right? So essentially say, well, this is a char argument. So one actually, so one push is enough, right? You can say, why can't you derive this from this, for example? Because you say, look, I already have this string, so I can generate this push, right? But then your classmate actually is right. He says, okay, but what if I suddenly add int b here, and then this compiler will happily generate this, right? And it will crash at runtime because A just essentially takes one argument. And so this essentially helps you to type check, right? So essentially, knowing the signature of a function allows the compiler to check that the call site invocation is correct in terms of types, and from there, generate the correct call site. So essentially saying, okay, it takes one argument, so I only need one push, right? Agree with this? But it's totally doable. So like if you don't know what the function is doing, looking at this either header file or this line which has extern declaration of a function, the compiler knows how to compile the code for this file, for the main, without even any other knowledge about A.C. Right? Agree with this? Okay. Any questions? Let me stop here for a sec. Good. Just wanted to make sure that we understand this. Okay, cool. So what kind of code we essentially get out of it? Again, we get two object files. So the first one, and if you read those sections with like obj dump or read elf tool, it will tell you, okay, it will tell you that, okay, there will be two sections, a text section and a data section in this file, right? The text section itself is only 16 bytes. So x10 is 16, right? And wow, why is that? Because it's a very short program. It fits on this string. That's your main function. There is nothing else in this program, right? It fits in 16 bytes. Fine. You say, what else? Is there a data section? Wow, cool. Yeah, there will be a data section, also 16 bytes. They will right now start at address 0, and the data section, since the text is 16 bytes, follows it and starts at address 16, right? The code starts at 0 because, okay, that's the text section. So the main function, this label, starts at 0. Remember, my wonderful push instruction is 55. Not a big surprise. We say, okay, since we are accessing a global variable, which one is that? Do you know? What is here? Oh, it's a string, right? Because this is a call site to A, right? So you say, look, I'm trying to push string on the stack, right? So address of string on the stack, it's a pointer to char. So since it's sitting exactly at the address 16, right? So I'm pushing those addresses. So this is 16, right? And this is what your human readable assembly shows you. So you're pushing something from the address 16, right? So that's exactly this thing, the call side of A. And then you say, look, I do a call instruction, right? But since I don't really know that where the symbol A is, I will generate this unusual address. I'll put Fs here, right? Why do you think it generates this address instead of like zeros or instead of anything else? There is certain logic to this. So what is this number? FF, 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 F3. You can tell me. No, do we know what this number is? Can we convert to binary? What is that? I'll give you a hint. It's a negative number. Do you remember how to how negative numbers are represented? What is, for example, representation for -1? All Fs. Yeah. So what's the? How does it work? Why is it all Fs?
The sign symbols can be the very first F nearest the hex, which defines it as negative.
Hold on. Remember, it's like the formula is minus A is invert all bits of A plus 1. It's 2's complement, right? So if 1 is -1, so if you have 1, which is in binary is 0, 0, all zeros, just 1, right? You invert them, you get binary 1, 1, all ones, but 1, 0, right? But since you do +1, you in the end get all ones, right? And all ones is essentially all Fs, right? It's just a reminder again, like it makes sense to know what these numbers are, otherwise you will get confused debugging this thing. And so, okay, so it's literally, if you flip the bits, you will see that it's -13, right? Or minus XD in hex, right? And so what it actually encodes is it encodes exactly what it shows you here. It's a call back to entry point. Why it makes sense? Well, like I think compilers actually encode the code back to here, right? So essentially you will be looping on a function and then eventually you will run out of stack because you will call all the time. And when you see the crash, like you will see that, okay, the stack fault, I ran out of stack, your backtrace will show you that you're executing EAP at this app, like your instruction pointing will point to this instruction. You will probably understand that the relocation step failed or linking step failed, and you somehow ended up with a binary, which is incorrect. So what is this -13? So they take the address of the next instruction, which is specifically as like if this one is at the address 8 plus 5, it will be 13. 13 is D, and it relative to this address, it's -13 will land you back here, right? So it's IP relative address. Any questions? Again, it's just a side node, but nevertheless, it's nice to understand those addresses and how they get generated. Okay, let's keep moving. So we generated this call side for this string, right? So let's take a look at what is there for this A file, so a.c, right? So again, it has 2 data sections, right? So it will have 2 unresolved symbols, which will have to come from a standard library, right? That's why you include those headers. You say that, and those headers will have a signature of write. So the write function will be something like int write. First argument is int, second is a pointer to char pointer, and a third argument will be int size of an object, right? So, and it will be in one of those header files. And stringlen is also there, right? So that's why you will end up with 2 relocation entries. So you will have to call to stringlen, and you will call to write, right? So again, this is magically happens to be at the same address, so it's -13, and this is a different offset because we're currently at the address 16, right? So it will go again here, I would assume, right? And if you looked, you look at the size of the text section, it's some size, 1C, but the data section is empty because it doesn't have any global variables, right? So not surprisingly, the data section is empty. And if you again, so if we, since we already know what will happen when we try to link those together, we try to link main.c and a.c, right? We will combine the text segment, we'll combine the data segment, and somewhat optional, but since the page protection works at the page boundary and the page on x86 is 4 kilobyte, you can pad the text section and the data section to 4 kilobytes to make sure that, for example, the data section is readable and writable. This is data. But for example, your code section is only executable, and you prevent a certain range of vulnerabilities which try to modify your code by saying you cannot write into the code section. Once it's loaded, the page is marked as executable and sometimes even not readable, right? So to make sure that you can hide the code as well, right? Okay, so again, the same trick which I was showing before, we just merge, and this is the end result. Essentially, if you link those two together, file which has the text section, so it has a larger size, it starts at a specific virtual address, right? It has a data section, and so this started address 496 plus 20 for whatever reason, x20, and this starts at the 496 by 2 at the second page, right? So it's padded by the page, and this one will start at the third page. Why is that? Because BSS is like this one will be loaded from disk, and this one will be just generated, like just an extra page will be allocated in memory. So if I again erase all of it on the screen, so that's your end result. So you say, I will be calling A, right? So now A is placed at this address, 10B4. However, x86 allows you to, instead of using global addresses here, it allows you to use IP relative address. So essentially, if your IP is currently x10AC, this address, and this instruction takes 5 bytes, because it's a 5-byte instruction, the offset, the distance from the end of this instruction to the entry point of A is encoded here, and the distance happens to be 3 bytes. Agree? So it's relative to the IP. So this is specifically, there are multiple ways to encode call instructions, and this is what it means. If you look up the manual for x86 instruction, you will see that, okay, there might be different encodings, but one way is to essentially say relative 32-bit address, or relative 16-byte address, or absolute. You can use a register or a memory as well, right? Just don't get surprised that there are different encodings, but again, you'll see that this is what compiler gets generated. So again, relative addresses for streamlam, because they are now merged and they're sitting in at those addresses. Relative address for the write function, and don't forget that since you did this push of the string here, right? So now we have the address of a string. In our case, originally it was 10, which is hex for 16, right? Remember that the data section was starting at 16. Now this is sitting at this address, right? So this is the steps which essentially linker did for you to make sure that this executable is ready to run at this specific address, right? So this entry point of the program and this entry point and this address have to match, right? Any questions? Okay. Yeah. I mean, relatively easy, right? Although just one wrinkle here, note that something else is executing before main. This is what I was kind of mentioning a couple of times, and I'm still not ready to explain what is executing before main. We'll get to this, but what will be your guess? Why do you need to execute something before main? What? To push arguments? Not quite, because arguments are like, no matter if you have to push arguments for main, they already have to be somewhere pushed by exec, right? So most likely they're already on the stack ready for this function. But what is a couple of real reasons to do this? Like, I'll give you a hint. So who knows C++? Huh? Yeah, half of the class. Do you know you can have static constructors in C++? At what context you think they execute? C++ is not that language which says that, constructor can actually run in C++. In Rust, you can say, well, it doesn't run, it has to be declarative, like it has to be all zeros, for example. In C++, you actually have to execute them. So like maybe your constructor opens a file. If you have a logging library, which writes your trace to a file, right? This is where, in this context before main, it will execute those constructors. Surprisingly, C has a similar mechanism. So you can declare, because, okay, you were writing like tracing libraries in C as well before even C++. And you say, like, I have to open a file before this, because maybe the very first thing which you do in main is you like essentially do trace of some string, right? And it has to go into a file. File has to be open, right? Destructors will be, yeah, so here, like if you need some, so essentially after you exit from main. We'll get to this, but just like don't get surprised that main is not the first function which got executed. So mostly it's to set up some environment for main. Okay, got it. So know enough. Let's take a look now at what these object files are. So how do we really keep this information in memory? Again, conceptually, object files are reasonably simple, right? So there will be some kind of a header, which at the beginning of a file will have some kind of a magic here saying that when you look at it, the operating system will check that this magic number matches. So it's really an L, for example. And conceptually, you only have this five kinds of information. The header itself, which says, okay, I have those sections inside of a specific sizes. I have a code, and of this size, maybe name of a source file, creation date. Then there will be actual code section here, right? Object code. You need this relocation information because remember, somewhere, remember we did push of a string here. We need to remember that we have to come back and patch this address. If we don't, the program will crash, right? So this relocation information is there in that file, and it essentially keeps track of what needs to be patched and how. Like, for example, if you move the data section, it will tell you, then add this move distance, then you will be golden. There will be another section here which holds information about symbols, like the functions which are provided in this, provided by these object files, as well as the symbols which are unresolved and have to be found somewhere else. And conceptually, yet another piece here will be debugging information, right? So essentially, when you generate code with debug info, which allows you to single step a program and still see the source lines, this information will be saved there in this object file, right? So conceptually, one of the early formats was called AOut, and that's the historic reason when you just invoke a GCC compiler, it spits out a file which looks like that, AOut. In practice today, it's actually an L file. It just has this name, AOut, right? But AOut was this very simple container format, which had a header, text section, data section, and those other relocation information and debug symbols here, right? So literally, if you wanted to read an out header, the header was declared as this, like a magic number at the very beginning, size of the text section, size of the data section, size of the BSX section, size of the symbol table, an entry point from which the program has to start executing. So essentially, like you, roughly speaking, this either main or whatever you wanted to execute at the entry point, and the sizes of the relocation sections for the text and data. Right? So relatively easy. However, it wasn't flexible enough. And people said, okay, it's good enough to just essentially load a program in memory. So if you had an AOut file generated by the GCC compiler, it has a header, literally says, okay, yeah, I know that I know that it has a text section somewhere in that file, and essentially, like there will be, since you know it follows the header immediately, you say, look, I will just copy from the file into memory of a process, right? And following that, there will be a data section, and since I know the size of this one, I know where the data section is. I will follow it. I will copy it here. Then later on, you say, look, I know the size of the BSS section. It's not here on disk, right? So I just like allocate memory and initialize it with zeros, right? But this will be my global variables initialized to 0, and then operating system will create a heap and a stack. And as I was saying, the stack will be growing this way, heap will be growing this way. This is address 0, for example. So kind of the layout of a process which we discussed in a previous, like early, like during the last lecture and early today, right? Any questions? Again, as I was saying, it was easy enough, but people said, okay, it's not really flexible enough to do all these sorts of things like represent shared libraries, represent static libraries, represent executable files, stuff like that. And they came up with yet another executable and linkable format, which is called ELF, right, for these letters, which kind of like was general enough to essentially represent all ranges of these use cases, right? And specifically, your homework will ask you to read a simple ELF file and load it in memory. So let's take a look at what this, what was the reason to come up with a new container format, right? So the reason was the following, that people said, okay, we want to hold different things in a single format, just because you can like use the same tooling to load it, relink it, do anything, right? And those different things are object files themselves generated by the compiler, executable files, which you either assemble or link from multiple object files, as well as static libraries and shared libraries, right? So remember this, this .a is an extension for the shared library, and .so is an extension for dynamically linked library or shared object, right? And we'll just take a look at what these are, but essentially, A-out didn't cut it, but ELF was good enough. So it was designed to hold all these formats, right? So concept or to A-out. So it will have an ELF header here, right? However, the main observation which they made is that there are two different things which happen to a file. The one major thing is to load the file in memory and start running it. And they said, okay, for this, we need slightly different set of information, right? So we roughly need something what describes what is executable memory, what is writable memory, and what is read-only memory. This way, the operating system can be very, very dominant. You will see it later in the x86 implementation when it does exec. It just literally says, okay, I will read the ELF header, will check the magic, and I will immediately switch to that view. I don't care about linking. I assume that everything is already linked for me. It simplifies implementation. That's why it's only like 10,000 lines of code versus like, you have a linker loader baked into the operating system. But it specifically immediately switches to this view, which is, in my diagram here, it's marked as green color. So it's called a program header table. So essentially, there will be a pointer in the header which points to the table, and this table is called program header table. And the entries in this table just describe how you have to load the things in memory, whether it has to be configured to be executable, read-only, writable, right? And you essentially, your exec file, exec implementation of the exec system call will just literally will be a loop which reads entries in this table, will check, okay, if it's executable, load it in memory at this specific address which it asks to, and just run it, right? And so, for example, these green lines essentially say, okay, all of this, there might be a couple of executable sections. So that init section runs your C++ constructors, which we just discussed a second ago. The text section actually runs your main function, right? But they're bundled together. And in terms of loading program in memory, we don't really care that they were two different sections. We just load it together in memory and just leave it there. And just since we have an entry point, which will point somewhere over here, we configure instruction pointer to point to this thing, and then operating system starts running it, right? So that's one view which ELF provides. Very simple. If your program is ready to run, you just load it in memory, even simpler than A out, right? And just run. However, if you say, okay, that's an object file, it's not yet ready to run, it will be linked, relocated, and stuff like that. There is a second view here, which is, if this is a program header table, the other one is called section header table. Typically, although I don't think it's strictly required, it's placed at the end of the file. That's why I draw it here. And it's, again, it's a table, which essentially says, I will have enough information about those blue sections, and it will describe how those sections have to be linked and loaded, like not loaded, but linked, relocated, right? So there will be like section like init text, relocation information, and stuff like that, right? So essentially, there's just two views, but they kind of separate what can happen to a file, right? It can be either linked or just loaded in memory, right? Or everything, right? If you like. That's why when you asked earlier today about what will happen with WC if cat depends on WC. Well, you can play a trick, and if it's really WC and cat says, okay, yeah, I depend on WC, as long as you have tooling to say, look, I will, instead of just blindly loading those green files, green sections into memory, I will do something with WC and load it in memory in a slightly more sophisticated manner, make sure that, you know, cat, which maybe depends on a function in WC, just essentially points correctly to like part of the stack section, right? So it's doable, but probably rarely done. Okay, so if we do something like this, so again, my GCC compiler, say just compile, again, skip position independent code, don't use built-in libraries, debug information which GDB can understand, because there are different debuggers and different formats for debug information, 32-bit code, do not omit stack frame pointer, and generate this hello elf.c. Then we do something like, say, invoke a linker, please, entry point will be a main function, link it at to run at address 0. So essentially, this guy will produce a out, like take this elf.o and produce a binary executable a out, right? So the elf header, which we can read with this read elf program, will look something like that. So it's literally the header of the elf file. So this is the long magic which operating system can check, saying that, okay, it's really an elf file, so there is no bug here. Some metadata, which is important, but what really we care about is this start of the program header and start of the section headers, right? So remember I said there will be a header itself, and there is no requirement, but somewhere in that file, there will be a program headers table. Right now, it's at this address 52 inside the file. And so when you do implement your exec or your loader, you look at this, you look at the elf header, you know where this field is in the header, you read this number, and from there you read your program header, right? So essentially you can do a loop from that over that table saying, okay, load this in memory, load this in memory, load this in memory. Then you'll take the entry point address. At this point, it's 0 because the text section will be loaded. There will be said, okay, load it at address 0. It will be loaded. If you follow correctly this protocol, you load it at address 0. And if you set the instruction pointer to address 0, you start executing and everything will work, right? And similar, like section headers will be at the end of the file at address 2980, right? Stuff like that. You also have size of the header, so 52 bytes. That's why it's not surprisingly matches this. Size of the program headers, 32 bytes. Actually, number of program headers too, stuff like that, right? So, and that's essentially my slide, which kind of like repeats what I said, that the program header table, so essentially this green one, which describes the view of how to load the program in memory. Don't link anything. used by the loader. Loader can be very, very simple. Simply read those sections, read this table, read this section from file, load in memory, run. And essentially, if you want to take a look at what's what's inside this table, so program headers, in this specific example, there will be just one loadable section, which will be readable, writable, and executable. Alignment requirements is 4 bytes. So it's an offset within a file is 74. Has to be loaded at the virtual address 000, right? So that's essentially the idea. That's what we will be doing in the homework, but there will be like a detailed description of how to do that, right? And the segment sections will be more sophisticated. So it will tell us, okay, there's a text section, read-only data, BSS, stuff like that, right? And essentially, this one is typically used by the linker. This information is used for merging and linking the code, as I was describing before, right? So not a big surprise, kind of. Okay, let me stop here. Any questions? Alf? Okay, not super hard conceptually. The devil is in the details, right? So there will be a good description of what to do during the homework, essentially, just how to write the code, which essentially reads the ELF file, loads it in memory, right? And in the there will be some additional information for what needs to be done. Okay, cool. So I have a couple of more examples, but again, the homework will kind of enumerate them all. Loading ELF, we kind of talked about it, and probably it's a good point to stop and start next lecture with understanding what the static libraries are and what the dynamic libraries are. So what's inside and how they're implemented.